The next 10 days of winter will be something we haven't witnessed in 4 decades. Right now, 3 seemingly unrelated forces are converging above North America. A super Arctic blast diving south, solar storms hammering our magnetic shield, and deep beneath California, the San Andreas is whispering warnings seismologists can't ignore. Scientists are calling this convergence unprecedented. The atmospheric river, the polar vortex split, the magnetic anomaly. When these collide, the next 10 days won't just rewrite weather records. They'll rewrite what we thought was possible. Stay with me until the end, because what's unfolding involves a cosmic connection nobody saw coming. Subscribe and follow along, because what unfolds during the next 10 days will reveal whether this is nature's tantrum or nature's warning shot. Because what happens when 40-year records break simultaneously isn't called a coincidence. It's called a pattern, and patterns have endings. Picture this: a weather map so angry, so sprawling, it looks like someone took a paintbrush, dipped in Arctic fury, and splashed it across 2/3 of the continental United States. We're talking Texas to Maine, Florida Panhandle to the Canadian border, a storm system so massive it has its own name, its own gravity, its own terrible momentum. Winter Storm Fern, they're calling it. And if you think that sounds quaint, like some elderly aunt who bakes cookies, think again. This storm is about to rewrite the rules of what winter means in America. Over 150 million people are in the path of this thing right now. That's nearly half the country. 35 states have already issued emergency declarations. Schools are closing days in advance. Airports are preemptively canceling thousands of flights. Hardware stores in Dallas and Atlanta, cities that barely know what a snow shovel looks like, have sold out of generators and pipe insulation. This isn't just a cold snap. This isn't just a snowstorm. This is the kind of meteorological event that gets studied for decades afterward, the kind that ends up in textbooks with a date attached to it, like the blizzard of 1888 or the polar vortex collapse of 2014. But here's what makes this different. What makes scientists lean forward in their chairs when they look at the data? The sheer convergence of factors. You've got Arctic air plunging south, yes, but you've also got moisture streaming in from the Pacific, moisture that normally wouldn't be there, colliding with this polar air mass in a way that creates the perfect conditions for catastrophic ice accumulation. We're not just talking about snow. Snow you can shovel. Snow you can plow. We're talking about ice, the silent killer of power grids, the thing that brings down transmission lines and leaves entire cities in the dark when the temperature is 10 below zero. The wind chill values being forecast for the upper Midwest are genuinely dangerous. We're talking about exposed skin freezing in under 5 minutes. Frostbite isn't a possibility. It's a certainty if you're outside unprepared. In some areas, forecasters are predicting wind chills of -40 to -50 degrees Fahrenheit. That's the kind of cold that makes your lungs hurt when you breathe. The kind of cold that makes your car refuse to start. The kind of cold that, frankly, most Americans alive today have never experienced. Now, you might be thinking, okay, but we've had bad winters before. What makes this the worst in 40 years? The answer lies in something called the polar vortex. And no, that's not just a scary term weather people invented to boost ratings. The polar vortex is real. It's always been there. And right now, it's doing something it rarely does. Imagine a massive river of air flowing around the North Pole, up in the stratosphere, circling like a protective barrier, keeping the Arctic cold where it belongs. That's the polar vortex. Most winters, it stays put. It does its job. But every so often, something happens in the atmosphere. Something involving temperature differences in the stratosphere, sea ice patterns, and atmospheric waves propagating upward from the surface. And that river of air gets distorted. It stretches. It wobbles. And sometimes it breaks. What we're seeing right now is a textbook polar vortex disruption, triggered by what scientists call a sudden stratospheric warming event. About 2 weeks ago, temperatures in the stratosphere over the Arctic spiked by more than 90 degrees Fahrenheit in just a few days. When that happens, the organized circulation of the polar vortex weakens, splits, or gets shoved off-center. And when that air mass, that reservoir of Arctic cold that's supposed to stay locked over the North Pole, gets displaced, it has to go somewhere. This time, it's coming south. All of it. At once. The last time we saw a polar vortex disruption this severe was back in January of 1985. Some of you might remember that winter. Record cold across the eastern United States. Citrus crops in Florida destroyed. Pipes bursting in homes that had never seen a freeze before. But here's the thing. Climate science has advanced since 1985. We have better models now, more satellites, more computing power. And those models are showing us something that should make everyone pay attention. This event, the one unfolding right now, has the potential to be even more severe than 85. The cold pool over Canada is deeper. The atmospheric setup is more persistent. And critically, the moisture feed from the Pacific is stronger, which means more snow, more ice, and more chaos. You want numbers? Fine. Let's talk numbers. Some areas of the Great Plains are looking at snowfall totals exceeding 2 feet. The ice accumulation forecast for parts of the Mid-South, places like Arkansas and Tennessee and Kentucky, is over an inch of ice. Do you know what that does to a power line? It doesn't just weigh it down. It snaps it like a twig. In Oklahoma and Texas, where the grid still hasn't fully recovered from the catastrophe of February 2021, authorities are warning of widespread, prolonged outages. Emergency management officials are setting up warming centers. Hospitals are checking their backup generators. This is the kind of preparation you see before a hurricane, not a winter storm. And then there's the travel nightmare. Interstate highways from Denver to Nashville to Richmond are expected to become impassable. Not difficult, not hazardous. Impassable. The FAA is already coordinating with airlines to pre-position aircraft away from affected airports because they know planes are going to be stuck on the ground for days. The economic impact of this storm, the lost productivity, the emergency response costs, the infrastructure damage, is projected to run into the tens of billions of dollars. We're talking about a weather event with GDP-level consequences. But maybe the most unsettling part isn't the storm itself. It's what it represents. For years now, scientists have been warning that a warming Arctic paradoxically leads to more extreme winter weather at mid-latitudes. It sounds contradictory, but the physics checks out. As the Arctic warms faster than the rest of the planet, the temperature gradient between the pole and the equator decreases. That gradient is what drives the jet stream, that high-altitude river of air that separates cold Arctic air from warmer air to the south. Weaken that gradient, and the jet stream gets wavier, meanders more, takes these big looping paths that can funnel Arctic air deep into regions that aren't prepared for it. What we're seeing this week might be a preview of the new normal. Winters that aren't just cold, but violently, historically cold, in short, intense bursts. So, when meteorologists say, this could be the worst winter weather in 40 years, they're not being hyperbolic. They're reading the data. They're watching the models converge. They're seeing something that doesn't come along very often, and they're sounding the alarm. The next 10 days are going to test the resilience of American infrastructure, the preparedness of emergency services, and the patience of every person who has to venture outside into this frozen hellscape. But here's what most people don't know, what the headlines aren't telling you. The cold and the snow and the ice, as catastrophic as they might be, are only part of the story. Because while all of this is happening on the surface, something equally extraordinary is happening above us, in space, where the sun is throwing its own kind of tantrum. And that's where things get really interesting. January 18th, 2026. While most Americans were checking weather forecasts and stockpiling bread and milk, the sun decided to make its own announcement. At 1437 Universal Time, a massive active region on the sun's surface, cataloged as AR 3592, unleashed an X 1.9 class solar flare. Now, if you're not familiar with solar flare classification, let me put this in perspective. X-class flares are the heavyweight champions of solar eruptions. They're the most intense category we have. An X1 flare has 10 times the energy of an M1 flare. An X2 has 20 times. This wasn't the biggest flare ever recorded, not by a long shot, but it was big enough to matter. Big enough to get every space weather forecaster in the world to sit up and take notice. But the flare itself wasn't the main event. Flares are essentially intense bursts of electromagnetic radiation, mostly X-rays and extreme ultraviolet light, that race across the 93 million miles between the Sun and Earth in about 8 minutes. They can disrupt radio communications, interfere with GPS signals, and generally make life difficult for satellites and astronauts. But they're over quickly. What really matters, what really has the potential to cause problems, is what often comes after. A coronal mass ejection, a CME. Think of a CME as the sun literally hurling a chunk of itself into space. We're talking about billions of tons of magnetized plasma, charged particles traveling at speeds of up to several million miles per hour, erupting from the sun's corona and spraying out into the solar system like buckshot from a cosmic shotgun. Most CMEs miss Earth entirely. Space is big, Earth is small, and the odds aren't great. But this one, the one that erupted on January 18th, didn't miss. It was what scientists call a full halo CME, meaning from Earth's perspective, it appeared as a bright halo expanding outward from the sun in all directions. Translation: it was headed straight for us. The impact came 48 hours later. On January 20th, instruments aboard NOAA's DS-COVR satellite, stationed about 1 million miles upstream from Earth, detected the arrival of the CME's shockwave. Within hours, Earth's magnetosphere, that invisible magnetic bubble that shields us from most of the sun's charged particle radiation, was getting hammered. NOAA's Space Weather Prediction Center issued a G4 geomagnetic storm watch. G4 is classified as severe, the second highest level on their scale. To put that in context, we maybe see 1 or 2 G4 storms in a typical year. They're rare, they're powerful, and they have consequences, but it gets better, or worse, depending on your perspective. Alongside the geomagnetic storm, forecasters also detected an S4 solar radiation storm. S4 is on a scale that goes up to S5, and we haven't seen an S4 level radiation storm in nearly 20 years. These events happen when high-energy protons accelerated by solar eruptions reach Earth, and they pose genuine risks. Airlines had to reroute polar flights to avoid exposing passengers and crew to elevated radiation levels. Satellite operators put spacecraft into safe mode to prevent damage to sensitive electronics. Astronauts aboard the International Space Station were advised to stay in more heavily shielded areas of the station. This wasn't a drill. This wasn't precautionary theater. This was real risk management in response to a real threat. And then there were the auroras. Oh, the auroras. Social media lit up with images of the northern lights visible as far south as Kansas, Missouri, even northern Arkansas. Skies glowing green and purple and red, dancing curtains of light that most people who posted those photos had never seen before in their lives. The aurora borealis is one of those phenomena that sounds magical, and it is, but it's also a symptom. It's what happens when charged particles from the sun collide with gases in Earth's upper atmosphere, exciting atoms and causing them to emit light. The farther south the auroras are visible, the more intense the geomagnetic storm. This was intense. Now here's where we need to pump the brakes a little bit, because there's a lot of misinformation floating around about solar flares and space weather, and I want to be clear. There is no established scientific link between solar flares, CMEs, or geomagnetic storms and surface weather patterns like the cold wave currently gripping the United States. None. Zero. The physics doesn't support it. Solar flares emit electromagnetic radiation that affects the ionosphere, the upper atmosphere, but they don't change atmospheric pressure systems or temperature gradients at the surface. Geomagnetic storms cause currents in the magnetosphere and can induce electrical currents in long conductors on the ground, like power lines and pipelines, but they don't make it snow. They don't cause polar vortices to collapse. Anyone telling you that the solar flare caused the winter storm is either misinformed or selling you something. But, and this is a big but, the absence of a known mechanism doesn't mean there aren't interesting questions worth asking. Science advances by exploring the boundaries of what we don't understand. And there are some genuinely curious correlations, some patterns that show up in the data that we can't fully explain yet. For instance, there's a small but persistent body of research suggesting that geomagnetic activity might, under certain conditions, influence atmospheric electric fields. Could those changes, subtle as they are, somehow interact with storm dynamics in ways we haven't fully characterized? Could the orientation of the magnetic field carried by a CME, specifically the direction of what's called the BZ component, matter in ways beyond just how deeply it couples with Earth's magnetosphere? These aren't mainstream ideas. They're speculative, but they're not pseudoscience either. They're frontier science, the kind of questions that require more data, better models, and open minds. What is absolutely not speculative, what is documented fact, is that intense space weather can wreak havoc on technology. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, caused telegraph systems across North America and Europe to fail. Some telegraph operators reported receiving electric shocks. Some telegraph lines could send messages even with their power supplies disconnected, powered by the currents induced in the wires by the storm itself. If an event of that magnitude happened today, in our hyper-connected, satellite-dependent, power grid-reliant world, the consequences would be catastrophic. Estimates suggest that a Carrington-class event could cause trillions of dollars in damage and take years to fully recover from. Power grids could be knocked offline for weeks or months. Communication networks could collapse. GPS would become unreliable or fail entirely. Modern civilization, it turns out, is remarkably fragile in the face of angry space weather. And here's the uncomfortable truth. We're overdue. The sun goes through roughly 11-year cycles of activity, oscillating between solar minimum, when the sun is relatively quiet, and solar maximum, when sunspots and flares and CMEs are frequent. We're currently in the early to middle stages of solar cycle 25, and it's already proving to be more active than many forecasters predicted. The X1.9 flare on January 18th is just one of several significant eruptions in recent months. Solar physicists are watching this cycle closely because the sun doesn't always follow the script. Sometimes it surprises us. Sometimes it reminds us that for all our satellites and models and early warning systems, we're still at the mercy of a star that's been fusing hydrogen for 4.6 billion years and doesn't particularly care about our infrastructure. So no, the solar flare didn't cause the winter storm. But the fact that they're happening at the same time, that we're dealing with both a historic cold outbreak and one of the most intense geomagnetic storms in years, that's worth noting. It's a reminder that Earth exists in a larger context, a solar system context, and sometimes multiple systems decide to act up simultaneously. It's also a reminder that we're playing a long game here. The sun will eventually throw a Carrington-level event at us again. It's not if, it's when. And when it does, the question is whether we'll be ready, whether we'll have hardened our grids and shielded our satellites and prepared our emergency response systems for an event that hasn't happened in over a century and a half. But maybe that's a conversation for another time. Because right now, while the magnetosphere is still reverberating from the January 20th impact, and while Winter Storm Fern is still dumping ice and snow across the heartland, there's a third piece of this puzzle that just landed on the table. And it's happening beneath our feet. Southern California woke up rattled, literally. Over the past 72 hours, seismologists have recorded hundreds of earthquakes clustered around the Coachella Valley, near the towns of Indio and Thousand Palms. The largest, a magnitude 4.9, struck early yesterday morning, strong enough to jolt people out of bed, strong enough to knock items off shelves, strong enough to make everyone in the region suddenly very aware of where they keep their emergency supplies. But here's the thing about earthquake swarms. They don't follow the normal rules. In a typical earthquake sequence, you get a main shock, a big one, followed by a series of aftershocks that gradually decrease in magnitude and frequency. It's like dominoes falling after the first big push. But swarms are different. Swarms are clusters of earthquakes without a clear main shock, without an obvious starting point. They just start happening, dozens or hundreds of them, often over the course of days or weeks, and then they stop. Or they don't stop. And that uncertainty is what makes them unnerving. The Coachella Valley sits in a geologically complicated neighborhood. You've got the southern terminus of the San Andreas Fault to the west, the San Jacinto Fault running through the valley itself, and a spiderweb of smaller faults threading through the region. This is the place where tectonic plates are actively grinding past each other, where the Pacific Plate is sliding northwest relative to the North American Plate at about 2 inches per year. That might not sound like much, but 2 inches per year, sustained over millions of years, built the mountains and valleys and faults that define Southern California. And all that motion creates stress. Rocks don't slide smoothly. They stick, they strain, and eventually they slip. That's an earthquake. Swarms, though, are a little different from your standard fault slip. They often occur in areas where fluids, water or magma or both, are moving through the crust. The fluid pressure can lower the effective stress on a fault, making it easier for small sections to slip. You end up with this cascade of little earthquakes, each one potentially triggering the next, as the stress redistributes through the rock. In some cases, swarms peter out on their own. In other cases, and this is what keeps seismologists up at night, a swarm can be a precursor to something larger. Not always, not even usually, but sometimes. The Brawley seismic zone, which is part of the same fault network, has a history of swarms. There was a notable one in 2012. Thousands of small quakes over several weeks, the largest around magnitude 5.4. That swarm eventually quieted down without producing a major event. But here's what scientists don't know. What they can't predict with any certainty. Whether this current swarm is just the crust adjusting, relieving stress in a relatively benign way, or whether it's loading stress onto a nearby section of fault that's already close to failure. It's the seismic equivalent of playing Jenga. Every small earthquake removes a little bit of stress from one place and adds it to another. Eventually, you pull the wrong block, and the whole thing comes down. And let's be honest about what we're really talking about here. The San Andreas Fault. The big one. It's the boogeyman of California geology, the event that everyone knows is coming, but nobody knows when. The southern section of the San Andreas, from the Salton Sea up through the San Gorgonio Pass and into the Mojave Desert, hasn't ruptured in a major earthquake since 1680. That's over 340 years. Meanwhile, the northern section, the part that runs from San Juan Bautista up through San Francisco and beyond, last ruptured in 1906. That was the Great San Francisco Earthquake, magnitude 7.9, one of the most devastating natural disasters in American history. The southern section is overdue. Statistically, geologically, by every metric scientists use to assess earthquake probability, The southern San Andreas is locked, loaded, and ready to go. The question isn't if, the question is when. So when hundreds of earthquakes start popping off in a swarm near the southern San Andreas, people pay attention. Emergency managers review their response plans. Seismologists pore over GPS data and INSAR measurements and seismograms, looking for any signal that might tell them what's happening at depth. Residents check their earthquake kits, make sure they have water and food and flashlights, and try not to think too hard about the fact that they live on top of one of the most seismically active regions on the planet. But here's the maddening part. Earthquake prediction doesn't work. We can't do it. We can identify faults that are likely to rupture. We can estimate the probability of a large earthquake occurring within a given time frame, say 30 years. But we cannot tell you that an earthquake will happen tomorrow, or next week, or next month. The physics is too complicated, the uncertainties too large, the system too chaotic. Earthquake swarms, for all the anxiety they produce, don't give us a crystal ball. There are, of course, fringe theories. There always are. Some people point to electromagnetic signals detected before earthquakes, arguing that changes in the Earth's crust generate electrical currents that could, in principle, be measured and used as precursors. Others talk about animal behavior, the old stories of dogs barking and birds flying away before a quake hits. And then there are the really far-out ideas, the ones that invoke cosmic rays or planetary alignments or solar activity as triggers for earthquakes. The mainstream scientific community doesn't give these ideas much credence, and for good reason. The evidence is weak, the mechanisms are poorly defined, and extraordinary claims require extraordinary evidence. But the human mind craves patterns. We want to believe that if we could just measure the right thing, observe the right signal, we could predict the unpredictable. We can't. At least not yet. What we can do is prepare. California has some of the strictest building codes in the world, specifically designed to withstand major earthquakes. Earthquake early warning systems can give people tens of seconds of notice before shaking arrives, enough time to drop, cover, and hold on. Emergency response networks are trained and ready. But even with all that preparation, a magnitude 7 or 8 earthquake on the southern San Andreas would be a catastrophe. Buildings would collapse, highways would buckle, water and power and communication lines would fail. The economic cost would run into the hundreds of billions. The human cost, in terms of injuries and displacement and disruption, would be staggering. And it's not a matter of if, it's a matter of when. So here we are. 3 seemingly unrelated events, happening within days of each other. A historic winter storm driven by a polar vortex disruption. A severe geomagnetic storm triggered by a solar eruption. An earthquake swarm in Southern California near one of the most dangerous faults on the planet. Are they connected? Almost certainly not by any direct physical mechanism. The atmospheric dynamics that drive winter weather operate on completely different timescales and energy scales than the solar activity that causes geomagnetic storms, which in turn operate on completely different timescales and energy scales than the tectonic stresses that cause earthquakes. These are independent systems. They don't talk to each other. They don't coordinate. But here's the thing that makes this moment so fascinating, so unnerving, so ripe for speculation. They're all happening at once. And when multiple low probability events stack up in a short time window, the human brain starts looking for connections. We're pattern-seeking machines. We evolved to find causes and effects, to identify threats, to make sense of a world that often seems random and hostile. So when the ground shakes, while the sky glows with auroras, and snow piles up in places that rarely see snow, we wonder. We ask questions. We look for explanations, even if those explanations require us to venture into territory that mainstream science hasn't fully explored yet. And maybe that's okay. Maybe that curiosity, That willingness to ask uncomfortable questions is what drives science forward, because the universe is under no obligation to make sense to us. It's under no obligation to keep its disasters neatly separated. Sometimes everything just goes wrong at once, and all we can do is watch and measure and try to understand. The next 10 days will test us in ways we haven't been tested in 40 years. And honestly, we're only just beginning to understand why. The polar vortex sounds like something out of a disaster movie, doesn't it? Some terrifying force that descends from the Arctic to freeze entire continents. And honestly, that's not entirely wrong. But the reality is both more complicated and more fascinating than any Hollywood script could manage. So let's talk about what this thing actually is, because understanding the polar vortex is key to understanding why the next 10 days are going to be so brutal. Imagine you're standing at the North Pole, looking up into the stratosphere, that layer of atmosphere that sits roughly 10 to 30 miles above the surface. Up there, circling the pole like a massive atmospheric whirlpool, is a river of air moving at speeds that can exceed 200 miles per hour. That's the polar vortex. It's not a storm. It's not a weather system in the traditional sense. It's a semi-permanent feature of atmospheric circulation, strongest during winter, when the temperature contrast between the polar regions and mid-latitudes is at its maximum. The vortex acts like a containment system, a fence that keeps the coldest air locked over the Arctic where it belongs. Most winters, this system does its job admirably. The polar vortex spins along the jet stream, that lower altitude river of air that separates cold polar air from warmer air to the south, maintains a relatively smooth west to east flow, and temperatures in the mid-latitudes stay within normal ranges. Sure, you get cold snaps, you get winter storms, but they're manageable, they're predictable, they fit within the bounds of what we consider normal winter weather. But every so often, something goes wrong. The vortex weakens, it distorts, and sometimes it completely falls apart. What triggers a polar vortex disruption? The answer involves something called a sudden stratospheric warming, or SSW for short. These events are exactly what they sound like: rapid, dramatic increases in temperature in the stratosphere over the Arctic, sometimes as much as 90 degrees Fahrenheit in just a few days. Now, you might be thinking, wait, warming in the stratosphere causes cold at the surface? How does that make sense? The answer lies in what that warming does to the circulation. When the stratosphere warms suddenly, the temperature gradient that drives the polar vortex weakens. The winds slow down. The vortex, no longer tightly organized, begins to wobble and stretch. In extreme cases, it splits into two or more separate circulation centers, or it gets displaced entirely off the pole, shoved southward into regions where it has no business being. And here's where it gets interesting. The stratosphere and the troposphere, the lower layer of atmosphere where we live and where weather happens, are coupled. They influence each other. When the polar vortex weakens or splits in the stratosphere, that disruption propagates downward over the course of days to weeks, affecting the jet stream and allowing Arctic air to spill southward. It's like opening a freezer door. All that cold air that was contained suddenly finds a path of escape, and it flows toward regions of lower pressure, which in this case means the United States. The sudden stratospheric warming that kicked off this current event happened in early January. Temperatures in the stratosphere over the Arctic spiked by more than 90 degrees Fahrenheit between January 4th and January 8th. Forecasters watched as the polar vortex, previously centered over the North Pole, weakened and began to elongate, stretching like taffy pulled in opposite directions. By mid-January, the vortex had effectively split into two lobes, one over Siberia and one over Canada. And that Canadian lobe, that reservoir of bitterly cold air, is now sagging southward, dragged down by the distorted jet stream pattern that the SSW created. But wait, there's more. Because the jet stream itself, that boundary between cold and warm air masses, isn't behaving normally either. Under typical conditions, the jet stream flows in a relatively straight west to east pattern, maybe with a few gentle waves. But when the polar vortex weakens, the jet stream gets amplified. The waves get bigger, deeper, more exaggerated. Meteorologists call this a highly meridional flow pattern, which is a fancy way of saying the jet stream is taking these huge north-south excursions instead of staying on a nice, smooth east-west path. And when you get a deep southward dip in the jet stream, you create a pipeline for Arctic air to flood into regions that normally don't see those kinds of temperatures. Right now, the jet stream has a massive trough, a southward dip extending from Western Canada all the way down through the central United States. That trough is acting like a conveyor belt, continuously funneling Arctic air southward. But here's where the situation gets even worse. At the same time that Arctic air is pouring south through the trough, moisture is streaming in from the Pacific and the Gulf of Mexico. You've got this setup where bone-dry, bitterly cold air is colliding with moisture-laden air, and that collision zone is where winter storm Fern is being born. The result is a multifaceted nightmare. Heavy snow on the northern edge, where temperatures are well below freezing, and freezing rain and ice accumulation on the southern edge, where temperatures are hovering right around the freezing mark. Forecast models are showing that this pattern isn't going to break down anytime soon. In fact, some extended range forecasts suggest the polar vortex might split again later this month, potentially setting up a second wave of Arctic cold in early February. This isn't a one-and-done cold snap. This is the beginning of a potentially prolonged period of abnormally cold weather that could extend well into late winter. And that has implications beyond just discomfort and inconvenience. Prolonged cold stresses infrastructure, heating demand spikes, straining natural gas supplies and electrical grids. Roads that go through repeated freeze-thaw cycles develop potholes and damage. Water pipes in homes and businesses subjected to sustained sub-freezing temperatures are more likely to freeze and burst. The longer this goes on, the worse the cumulative impact becomes. There's also the question of what's driving these sudden stratospheric warmings in the first place. Scientists have identified several factors. One is the propagation of planetary waves, large-scale atmospheric waves that originate in the troposphere and propagate upward into the stratosphere. These waves can disrupt the polar vortex circulation, weakening it or even reversing it temporarily. Another factor is the state of the Arctic itself. Sea ice extent has been declining for decades due to climate change, and some research suggests that reduced sea ice can influence atmospheric circulation patterns in ways that make polar vortex disruptions more likely. There's also evidence that tropical weather patterns, specifically the phase of the Madden-Julian Oscillation, can influence stratospheric dynamics. The atmosphere is a coupled system, and changes in one region can cascade through the entire global circulation. What's becoming increasingly clear is that polar vortex disruptions may be becoming more frequent as the Arctic warms. This seems counterintuitive at first. A warmer Arctic should mean less cold air available, right? But what matters isn't the total amount of cold air, it's how that cold air is distributed. If a warming Arctic leads to more frequent disruptions of the polar vortex, you end up with a situation where the Arctic itself may be warmer than normal, but mid-latitude regions experience more frequent and intense cold outbreaks. It's not that winters are getting colder overall, it's that they're becoming more variable, more extreme, with bigger swings between warm and cold periods. And for infrastructure and emergency management and human safety, extreme variability is often worse than consistent cold. So that's where we are. The polar vortex has broken down. The jet stream is in chaos. Arctic air is flooding south. And for the next 10 days at minimum, possibly longer, a huge swath of the United States is going to experience winter weather that most people alive today have never seen before. The science behind it is well understood. The mechanisms are clear. But understanding doesn't make it any less dangerous. And it doesn't make the cold any less cold. What it does do, hopefully, is give us a framework for understanding why this is happening and what it means for the future. Because if polar vortex disruptions are becoming more common, then what we're experiencing right now isn't an anomaly. It's a preview. Cold air alone doesn't make a historic winter storm. You need moisture. You need that collision between frigid Arctic air and warm, water-laden air from the tropics and subtropics. And right now, that collision is happening in spectacular fashion across a huge portion of the United States. This is the piece of the puzzle that transforms a simple cold outbreak into a multi-state disaster. The element that turns inconvenience into catastrophe. So let's talk about where all this moisture is coming from and why it's showing up in exactly the wrong place at exactly the wrong time. The Pacific Ocean is a vast engine of moisture transport. Water evaporates from the ocean surface, particularly in the subtropics where sea surface temperatures are warmest, and that moisture gets caught up in atmospheric circulation patterns and transported eastward toward the North American continent. Under normal winter conditions, much of that moisture gets wrung out as precipitation when it hits the mountains of the Pacific Northwest and the Sierra Nevada. What's left, the air that makes it over the mountains, is typically drier and less capable of producing significant precipitation. But this week, the atmospheric setup is anything but normal. There's an atmospheric river aimed directly at California right now, a long, narrow corridor of concentrated moisture flowing from the tropical Pacific toward the west coast. Atmospheric rivers are responsible for most of the heavy precipitation events in California, and this one is particularly robust. Satellite imagery shows a continuous plume of water vapor stretching from near Hawaii all the way to the California coast, a fire hose of moisture pointed at the western United States. Normally, this moisture would dump as rain or snow in the mountains and dissipate. But the jet stream pattern that's funneling Arctic air southward through the central United States is also creating a pathway for some of that Pacific moisture to stream inland, over the Rockies, and into the Central Plains. At the same time, there's moisture streaming northward from the Gulf of Mexico. A southerly flow ahead of the Arctic cold front is pulling warm, humid air from the Gulf up through Texas and into the southern plains and the Mississippi Valley. This Gulf moisture is running headlong into the Arctic air mass moving south, and that collision zone is where things get ugly. When you have warm, moist air overrunning cold air at the surface, you create conditions for freezing rain and ice accumulation. The warm air aloft causes precipitation to fall as rain, but when those raindrops pass through a layer of sub-freezing air near the surface, they supercool. They're still liquid, but they're below 32 degrees Fahrenheit. And when those supercooled drops hit anything, trees, power lines, roads, cars, they freeze instantly on contact. Ice storms are among the most destructive types of winter weather. They don't have the dramatic visual impact of a blizzard, no whiteout conditions or massive snowdrifts, but they cause incredible damage. A quarter inch of ice accumulation is enough to bring down small tree branches and cause scattered power outages. Half an inch can snap larger branches and cause widespread outages. An inch of ice, which is what's being forecast for parts of Arkansas, Tennessee, and Kentucky, is catastrophic. Power lines that were designed to handle a certain load of ice and wind can't handle that much weight. They sag, they swing in the wind, and they snap. Transformers fail. Substations go offline. And when the power goes out in the middle of a historic cold snap, people die. The National Weather Service has already issued ice storm warnings for over 15 million people across the Mid-South and Lower Ohio Valley. These aren't watches or advisories, they're warnings, the highest level of alert, meaning significant ice accumulation is expected and impacts are imminent. Emergency management agencies in affected states have been mobilizing for days. Power companies have brought in crews from outside the region, pre-positioning them so they can respond quickly when the outages start. Because, make no mistake, the outages are going to start. This isn't a question of if, it's a question of how many and how long. Meanwhile, on the northern edge of this storm system, where temperatures are well below freezing and staying there, you've got heavy snow. Not the light, fluffy powder that skiers love, but heavy, wet snow driven by strong winds. Blizzard warnings are in effect from Nebraska through Iowa and into Wisconsin and Michigan. Visibility will drop to near zero at times. Winds gusting to 50 miles per hour will create massive snowdrifts. Roads will become impassable, not because they're not being plowed, although there's only so much plowing you can do in a blizzard, but because cars will get stuck, jackknife semis will block highways, and emergency vehicles won't be able to reach people who need help. The snow totals being forecast are staggering. Parts of Kansas and Missouri are looking at 18 to 24 inches. Southern Wisconsin could see over 2 feet. These are numbers you typically see in major nor'easters along the East Coast, not in the Midwest, and the snow is only part of the problem. The wind is going to cause extensive drifting, making some roads impassable even where snow totals are lower. Rural areas, which often have limited snow removal resources to begin with, could be cut off for days. Then, there's the eastern seaboard. As this massive storm system slowly shifts eastward over the next several days, it's going to interact with moisture coming off the Atlantic Ocean. The result is going to be a nor'easter-style event for the mid-Atlantic and Northeast. Major cities like Washington, D.C., Philadelphia, New York, and Boston are all in the potential impact zone. Forecasters are still working out the exact track of the system, and track matters immensely with East Coast winter storms. A shift of 50 miles north or south can be the difference between a foot of snow and a cold rain. But what's becoming increasingly clear is that the coastal storm is going to be phasing, combining, with the main system coming out of the interior. And when that happens, you get what meteorologists call a bomb cyclone, a storm that intensifies rapidly and produces extreme impacts. The moisture dynamics of this event are being driven by sea surface temperatures that are, in many areas, above normal. The Gulf of Mexico is warmer than average for mid-January. The Atlantic off the East Coast is warmer than average. And those warmer than normal waters mean more evaporation, more moisture available to fuel the storm systems that are developing. It's one of those uncomfortable ironies of climate change. A warming world can actually make individual winter storms worse, even as overall winters become milder on average. More moisture in the atmosphere means more fuel for storms, whether those storms are hurricanes in summer or blizzards and ice storms in winter. There's also the question of duration. This isn't a fast-moving system that's going to race through and be gone in 24 hours. The forecast models are showing this storm complex persisting for days, continuously drawing in moisture from both the Pacific and the Gulf and Atlantic, continuously colliding with Arctic air, continuously producing precipitation. Some areas could see precipitation in some form, whether snow, ice, or rain, for 4 or 5 consecutive days. The cumulative totals, the cumulative impacts, are going to be extraordinary. And then there's what happens after the storm. When you dump a foot or more of snow on a region, or coat everything in an inch of ice, the cleanup and recovery take time. Roads have to be cleared. Power has to be restored. But if temperatures stay well below freezing, which they will, that ice and snow aren't going anywhere. They're going to sit there, making life difficult until temperatures moderate enough for melting to begin. And in some areas, with the prolonged cold pattern forecast to persist, that might not happen for a week or more after the precipitation ends. The moisture collision happening right now is a textbook example of how winter storms develop and intensify, but it's being amplified by the extreme nature of the atmospheric setup. You've got all the ingredients in place at maximum intensity, and they're interacting in a way that's creating a perfect storm, literally. The forecasters who are calling this historic aren't exaggerating. They're not hyping it up for ratings. They're looking at the data and seeing something that doesn't come along very often. And that should concern all of us. While Winter Storm Fern batters the United States and the magnetosphere recovers from its solar pummeling, there's another revolution quietly unfolding in the world of space weather forecasting. It involves artificial intelligence, machine learning algorithms, and a complete reimagining of how we predict what the sun is going to do next. And if you think AI predicting solar storms sounds like science fiction, well, welcome to 2026. The future is already here. Traditional space weather forecasting relies heavily on physics-based models. Scientists input observations of the sun, solar wind conditions, and Earth's magnetosphere into computer models that solve complex equations describing plasma dynamics, magnetic field interactions, and particle acceleration. These models are sophisticated. They're based on decades of research, and they work reasonably well. But they have limitations. Physics-based models are computationally expensive, requiring supercomputers and hours of processing time to produce forecasts. They also rely on assumptions and simplifications that don't always hold true in the chaotic, turbulent environment of space plasma. And critically, they struggle with the rapid, nonlinear processes that can turn a relatively minor solar event into a major geomagnetic storm. Enter artificial intelligence. Machine learning algorithms, particularly deep learning neural networks, have proven remarkably good at identifying patterns in complex, high-dimensional data. And space weather data is nothing if not complex. You've got magnetic field measurements, particle flux data, X-ray and ultraviolet observations of the sun, solar wind speed and density, and dozens of other parameters all varying simultaneously. Human forecasters and traditional models can struggle to integrate all that information in real time. Neural networks can process it almost instantaneously and identify subtle correlations that humans might miss. Over the past several years, researchers have been training machine learning models on decades of space weather data. They feed these models historical observations of solar activity, measurements of solar wind conditions, and records of geomagnetic storm impacts on Earth. The models learn to recognize the patterns that precede significant events, and the results have been impressive. Some AI-based models can now predict the likelihood of a geomagnetic storm with greater accuracy than traditional physics-based models, and they can do it faster, with forecasts generated in seconds rather than hours. One of the most promising applications is predicting the arrival time of coronal mass ejections. When a CME erupts from the sun, forecasters need to know when it's going to hit Earth so they can issue warnings to satellite operators, power grid managers, and airlines. But CME propagation through the solar wind is complicated. The CME can accelerate or decelerate as it travels. It can interact with other solar wind structures. Traditional models give you a rough estimate, plus or minus 6 to 12 hours, which isn't bad, but isn't great when you're trying to coordinate a global response. AI models trained on past CME events can refine those predictions, narrowing the uncertainty window and giving operators more precise information about when to expect impacts. There's also the question of CME intensity. Not all CMEs are created equal. Some barely ruffle Earth's magnetosphere. Others, like the one that hit on January 20th, cause severe geomagnetic storms. The key factor is the orientation of the magnetic field embedded in the CME, specifically the direction of that B's component mentioned earlier. If the field is oriented southward, it couples efficiently with Earth's magnetic field and can drive strong geomagnetic activity. If it's oriented northward, the coupling is weak and the storm fizzles. But we can't measure the magnetic field orientation of a CME until it reaches the DSCO-VR satellite, 1,000,000 miles upstream from Earth, which gives us only about 30 to 60 minutes of warning before impact. That's not much time. Machine learning is also being applied to solar flare prediction. Forecasters analyze active regions on the Sun, looking at their magnetic complexity, size, and evolution to estimate the probability of flares. But the Sun is unpredictable. Active regions that look menacing sometimes stay quiet, while seemingly benign regions suddenly erupt. AI models trained on years of solar observations are getting better at identifying the subtle signatures that precede flares. They're not perfect. Predicting solar flares remains one of the hardest problems in space physics, but they're improving. Beyond prediction, AI is being used to fill gaps in observational data. Space weather monitoring relies on a network of satellites, but those satellites don't provide complete coverage. There are gaps in time and space where we simply don't have measurements. Machine learning models can interpolate, using the data we do have to estimate conditions in the gaps. They can also fuse data from multiple sources, combining observations from different instruments and satellites to create a more complete picture of the space environment. But despite these challenges, the trajectory is clear. AI is going to play an increasingly central role in space weather forecasting over the coming years. The combination of physics-based models, which provide interpretable results grounded in our understanding of the underlying processes, and AI models, which excel at pattern recognition and rapid prediction, is likely to be more powerful than either approach alone. We're moving toward a future where space weather forecasts are faster, more accurate, and more actionable. And given what we've just experienced with the January 20th geomagnetic storm, that future can't come soon enough. While AI learns to predict the Sun's tantrums, another set of spacecraft has been quietly revolutionizing our understanding of what happens when solar storms hit Earth. The Cluster 2 mission, a constellation of 4 identical spacecraft flying in formation through Earth's magnetosphere, has been operating for over 2 decades now. And the data it's collected has fundamentally changed how we think about the boundary between Earth's protective magnetic bubble and the harsh environment of space. This isn't just academic curiosity. Understanding magnetospheric dynamics is essential for predicting how severe a geomagnetic storm will be and what its impacts might be. Earth's magnetosphere is the region of space dominated by our planet's magnetic field. It's a teardrop-shaped bubble, compressed on the sunward side by the pressure of the solar wind and stretched into a long tail on the night side. The boundary of this bubble, called the magnetopause, is where Earth's magnetic field meets the solar wind. And that boundary is not static. It's constantly shifting, responding to changes in solar wind pressure and the orientation of the interplanetary magnetic field. During geomagnetic storms, when a CME or a high-speed solar wind stream impacts the magnetosphere, the magnetopause can be compressed dramatically, sometimes pushed inward by thousands of kilometers. For decades, scientists understood the magnetopause as a relatively simple boundary layer. Solar wind on one side, magnetospheric plasma on the other, with some mixing occurring through a process called magnetic reconnection. Reconnection is the fundamental mechanism by which energy and particles from the solar wind enter the magnetosphere. When the magnetic field lines in the solar wind and the magnetic field lines of Earth's magnetosphere are anti-parallel, pointing in opposite directions, they can connect and reconfigure, allowing solar wind plasma to flow into the magnetosphere. This process drives geomagnetic storms, fuels the auroras, and can pump enormous amounts of energy into the near-Earth space environment. But Cluster 2 revealed that the magnetopause is far more complex and dynamic than anyone realized. Because Cluster consists of 4 spacecraft flying in a tetrahedral formation, it can make simultaneous measurements at 4 different points in space. This allows scientists to construct 3-dimensional maps of the magnetic field and plasma conditions at the magnetopause, something that's impossible with a single spacecraft. And what they found was astonishing. The magnetopause isn't a smooth boundary. It's filled with structures, waves, ripples, and something called flux transfer events. Flux transfer events, or FTEs, are transient bursts of magnetic reconnection that create temporary magnetic tunnels connecting the solar wind to the magnetosphere. These events last only a few minutes, but during that time, they can transport significant amounts of plasma and energy across the boundary. Cluster data showed that FTEs occur far more frequently than anyone expected, essentially continuously when conditions are favorable for reconnection. This means the magnetosphere is constantly opening and closing, breathing in solar wind plasma through these transient portals. What Cluster found was that substorms are initiated by reconnection in the magnetotail, similar to reconnection at the magnetopause, but in reverse. Instead of opening the magnetosphere to solar wind, reconnection in the tail closes field lines and releases stored energy. But the process is incredibly dynamic and structured. Cluster observed high-speed plasma jets, intense electric fields, and turbulent fluctuations that traditional models didn't predict. The spacecraft also detected what are called dipolarization fronts, sharp boundaries separating stretched field lines from more dipole-like field lines closer to Earth. These fronts propagate earthward at high speeds, carrying energy and particles, and they're associated with the most intense auroral brightenings. Another major discovery from Cluster involves particle acceleration. Geomagnetic storms aren't just about pretty lights in the sky. They accelerate electrons and ions to very high energies, creating radiation belts around Earth that can damage satellites. Understanding how particles get accelerated during storms is critical for predicting radiation hazards. Cluster data showed that acceleration occurs through multiple mechanisms, including interactions with electromagnetic waves in the magnetosphere. The spacecraft detected chorus waves, Whistler mode waves, and electromagnetic ion cyclotron waves, all of which can resonantly interact with particles and boost their energies. The interplay between these different wave modes and different particle populations is incredibly complex, but Cluster's multi-point measurements allowed scientists to untangle some of that complexity. Perhaps most importantly, Cluster revealed that the magnetosphere is fundamentally a turbulent multi-scale system. There's structure and variability on scales ranging from thousands of kilometers down to just a few meters. Energy cascades from large scales to small scales, dissipating eventually as heat. This turbulence affects how quickly energy from the solar wind can penetrate into the inner magnetosphere and how efficiently particles can be accelerated. Traditional models that treat the magnetosphere as smooth and laminar miss all of this richness and likely underestimate storm impacts. The Cluster mission has been extended multiple times, far beyond its original planned lifetime, because the data it provides is so valuable. But the spacecraft are aging, instruments are failing, fuel for maneuvering is running low. Eventually, Cluster will end, and when it does, we'll lose our ability to make simultaneous 4-point measurements in the magnetosphere. There are plans for follow-on missions, constellations of smallsats that could provide even better spatial coverage, but those missions are still in development. In the meantime, scientists are racing to extract as much knowledge as possible from Cluster's datasets, analyzing years of archived observations to uncover patterns and processes that weren't understood when the data was first collected. The insights from Cluster have already been incorporated into modern space weather models, improving their accuracy and realism. But there's still so much we don't understand. The magnetosphere is a complex, non-linear system, and predicting its response to solar storms remains a challenge. Every major geomagnetic storm, like the one we just experienced on January 20th, provides new data, new opportunities to test our models and refine our understanding. And as we've seen, getting those predictions right matters. It matters for satellite operators, for power grid managers, for airlines, for anyone who depends on the technology that space weather can disrupt. Cluster didn't solve all our problems, but it gave us the tools to ask better questions. And in science, asking the right questions is half the battle.